First of all, we start off with a little bit of history, and you've probably heard of most of these folks. James Clerk Maxwell, he formalized the electrical theory of Lentz, Ampere, Gauss, and Faraday. And each one of the four Maxwell equations are from these various people. Maxwell did add a little bit to Ampere, just some fudge factors. Heinrich Hertz was the first one to take Maxwell's equations and actually make some antennas that worked. Unfortunately, his antennas were about yay big, and he was in the UHF range. So we all know there's a problem with UHF when you're building equipment. It's really hard to make it work. He actually did make it work, and this is where he started. When Marconi came along, he made antennas up to 1 kilometer long, and things got along much, much better. But later on, we went, oh, there's such a thing as skip, and 200 meters on down was what they gave the amateurs, and we found out shortwave worked. No one else thought about the ionosphere. But Heinrich Hertz produced and detected the first electromagnetic waves from Maxwell's work. His antennas were tuned at approximately 4 meters in the VHF range. He established the photoelectric effect, for which Einstein developed the theory and got his Nobel Prize, his first one, I do believe. Hertz's experiments explain reflection, refraction, polarization, interference, and the velocity of electric waves. Along comes Oliver Heaviside, who is self-taught, but he's fairly brilliant. I could give you a 3-hour lecture on what this guy did alone. He was a self-taught electrical engineer, mathematician, and physicist. He was the nephew of Charles Wheatstone, who happened to be the co-inventor of the telegraph, and more popularly known for the Wheatstone Bridge. He developed the telegrapher's equations, which you may or may not have heard of, but there was a problem with oceanic telegraphic cables, and there was a real problem with too much capacitance. Heaviside came along and said, well, why don't you just put some inductance in there to get rid of the reactance? And all of a sudden, when they worked up the corporate chain, they went, gee, maybe we should try some inductance, and it worked, and it was a commercial success. He got kind of miffed at that and wouldn't accept any patents nor any money for it either. So he died very penniless, even though he was very brilliant. He adapted complex numbers to the study of electrical circuits. Later on, we will see the complex plane, and we'll see inductance, resistance, and capacitance in their various orientations. He also invented coax, which I didn't know until I read this. He also predicted the existence of the ionosphere from Hertz's work and some of what Marconi did. If you look at the time frame here, Maxwell and Hertz died very, very young. They had a lot more good work in them, but they died young. Heaviside died an old man, as well as Nikola Tesla. Marconi, medium-age life, but he was working Marconi, in fact, right now. But first, Heaviside also developed a condensation of the Maxwell equations. Maxwell originally wrote in quaternions, which are really abstruse mathematics, which he got yelled at by the mathematical community, and they said, please put this into calculus. Well, Heaviside and a guy named, what was his name? Lawrence and Gibbs of Gibbs Free Energy fame came along and they simplified it. But 20 equations and 20 unknowns into 4 equations and 4 unknowns doesn't make a lot of sense to me. A whole bunch of information got thrown out, and what we call the Maxwell equations is a tiny little bit of the information that he had in his original equations. But they define all of modern electronics. He also developed a vector calculus and all the operations and operators in vector calculus, which we'll see in a few slides from now. I'm not even going to attempt this guy's first name. Mr. Marconi won a Nobel in physics in 1909. Which
Guglielmo.
There's an R in there?
Guglielmo. Yeah, that's it.
The R is silent.
Mr. Marconi actually got a lot of his money from the Jameson whiskey dynasty. His mother was of the Jameson family, and she inherited, I think, half of the Jameson wealth. So she was Irish, married to an Italian who produced the Guglielmo, and he, being a little rich kid, grew up with tutors. So he didn't have to really go to school, but he read, as well as Oliver Heaviside and Harris, read Maxwell's and went, gee, this is pretty interesting stuff. I want to do this. And Marconi also said, well, the Hertz work looks good, but what happens if we use really, really long antennas? So he came up with antennas that were multiple kilometers long, and he made it work on very, very simple means. But he was also stepping on Nikola Tesla's toes, because Tesla developed a lot of the radio, like the coherer, some of the spark gap circuits were all done by Nikola Tesla, and he patented everything. He worked with Edison early on when he first came over from the old country, and patent was everything Edison did. He made sure to patent every idea he had, even if it was kind of silly. And he also made a lot of money on royalties. Tesla made a lot of money on royalties too, and he was a fairly wealthy man, but being wise, he used other people's money to do a lot of his work. I could speak for another 3 hours just on Tesla. I'm going to skip over him, but basically he held the patents on a lot of the work that Marconi did. So, onward. Maxwell's equations. I've already touched on this, but 20 quaternion equations and 20 unknowns. Quaternions are basically in 4 space. So, vector calculus normally is done in 3 space, even though it can be done in n-dimensional space. He used quaternions, which are normally 4 space. And then Heaviside, Lawrence, and a guy named Gibbs came along and said, well, we can make these look more mathematical and make the mathematical community happy. Maxwell got a lot of grief, and he was reworking all of his material until the day he died. He died of intestinal cancer. I think he was 40 years old. Unfortunately, he had a lot of good work left, but it didn't get published. It's still in his papers, though, if you want to dig. These are the 4 equations that did survive, and this is the vector form of each one. I'm going to go through them slowly, but first of all, you're going to notice epsilon 0 and mu 0. Epsilon mu. One interesting thing is, if you take mu 0 times epsilon 0, take the square root and invert it, you get the speed of light. It's one of those things that just kind of pops out magically, and you go, how did that happen? It happens all over in physics. Why does it do this? But epsilon 0 is the electrical permittivity in free space, and it's in farads per meter. Mu 0 is the permeability in free space, and it's in henries per meter. This is what you're going to need to know for reactance. One of these is for inductance, the other one's for capacitance. I could give you the numbers, but you can look those up. It's unimportant. The first equation, this is in a static mode. This is an electrostatic equation. This describes a capacitive field, an electric field that is in a capacitor. This is from Gauss's law of electricity. Gauss is a famous German mathematician, and he examined a lot of physics, and he came up with and put his name on lots and lots of laws. Del dot E is actually a divergence operator, and it's kind of like everything pointing out from a single point in space. It shows you how much does something increase. What is the strength from a point source outward? That's all that says. And it's rho over epsilon 0. And unfortunately, I forgot to write down rho. It's a density of a field. Excuse me. Next, we come along to the Gauss's law for magnetism. And this is also a divergence operator in a magnetic field. There is no divergence in a magnetic field because it's not a monopole, meaning There's a north pole and a south pole to every